Papa Flammy's Advent Calendar.
Here. Morning, fellow mathematicians! Welcome back to another video! Today's video is going to be very exciting on the Advent Calendar. This got requested a lot and it took a huge amount of time to get a hold of this very book that we are going to take a look at today. Richard Feynman, the man himself, claimed this book that we are going to review today to be the most cherished mathematics resource of the last century, which really has to say something if you consider Feynman himself saying this. And I was contacting the University of Princeton. This is where he was a research assistant back in the days, in the 40s. Start of the 40s, if they could hand this book over to me, if they can find it in their archives, and they actually did. We are going to review it today. But before we get into that, I would like to tell you guys that you can win this very book today. During the video, letters will pop up once again, just like this one right here. This will be part of the solution phrase. Put all the letters together and send it over to me to pi=3@papaflammy.engineer to basically get a place in the giveaway. And then I'm going to announce the winners at the end of the year, or the winner. It's only going to be one winner after all. Also, don't forget to check out stemmerge.eu. I just recently released the Cyber Tensegrity, the illegitimate child of Elon Musk and I. Definitely make sure to check it out to support the channel this way. Link down in the description too. And now we are going to dive right in. And the book that we are going to cover today is the one mathematics resource that you should all have lying at home. It's the It's the Manga Guide to Linear Algebra. I have reviewed the Manga Guide to Physics before and to Calculus, and now it's finally time for Linear Algebra. I already said it on the live stream before, but I hope I got some of you really good with the clickbaity thumbnail and everything. But on a serious note though, those manga guides are actually not too shabby. They are actually a really good resource for getting started in the topic. And today, Linear Algebra and this one had really good reviews, better than the physics one. So let's dive right in and let's take a look at it. Believe it or not, but the Manga Guide series is actually a really good resource for learning mathematics in the first place. And they have a huge repertoire of basically courses that are being covered in their books. And they do not only do like basic stuff like calculus and linear algebra, they also go into quantum physics and all this crazy stuff, special and general relativity, all of this good stuff. So you should definitely check them out. And if you don't have them in your bookshelf already, make sure to get yourself some of these. They are only like 10 to 20 bucks per book, which is totally fine. So yeah, definitely make sure to check them out. They are also available in Japanese. This is like the mother language of these books, written in Japanese by Takahashi. And yeah, let us take a look at the first few pages, at the contents of this book. So this right here is the cover. This is the Echi main character that we are going to deal with, which is going to be fucked in the ass, I suppose, at some point by this old guy. This is how most of the Japanese things go in a normal case. And this right here is the random character with the 2 meter long dick. So at first, Manga Guide to Linear Algebra. Okay, yeah, praise for the Manga Guide series. There are a lot of these. Take a look at all of these, this is crazy. Let's take a look at the content. So at first a little overview what linear algebra actually is, and then they are going to take a look at the fundamentals. Fundamentals being probably all the logical stuff like implications, equivalences, tiny little bit of set theory, and then going into functions. After that already comes an intro to matrices, which it's really quick. In a normal case you should cover groups and semi-groups and all of this before, but let's see how they are going to manage this one. And after that, even more matrices. Introduction to vectors. Okay, in a normal case, vectors should come before matrices and determinants, but never mind. Then linear transformations and eigenvalues and eigenvectors. This is the section that I'm most excited about, and I want to see how they perform on this behalf. Preface. This book is for anyone who would like to get a good overview of linear algebra in a relative short amount of time. Exactly, this is what the book is here for. Prologue. Let the training begin, desu. Okay, let's see. Whoa. Hanamichi University. Okay, nothing to be afraid of. It's now or never. Oh, it's already getting pretty intense on the first page. Oh, and there we have the anime character who's going to fuck the side character in the ass at some point. Excuse me, I'm there, Nietzsche. What do we have here? Oh. He's going to unpack his Sharingan, I suppose, in the next chapter. This guy is no fun to deal with, I suppose. I'm a freshman. My name is Reichi Yurino. Would you, by any chance, be a Tetsuo Ichinose Karate Club captain? Indeed. I can't back down now. Wow, the Hanamichi Hammer himself. This is what the girls call a stick, I suppose. Oh yeah, see? They are already kicking him in his huge cock. Are you serious? Okay. Please, I want to get stronger, Desu. Oh, you've seen my book? Mathematics for Everyone. Author Reichi Yurino, or the guy himself, the boy himself has done it. He created his own book. Okay, under one condition, blah blah blah. You have to tutor my little sister in math. Yeah, this is how all good hentai is starting. Awesome. So this was the prologue. Now we know what the guy's name is. I already forgot it once again. And now let's start with what is linear algebra. Let's see. Okay, so he got kicked in the spot once again. And then we have to take a look at Misa Ichinose. Okay, this is the little sister. She is pretty edgy days. I had no idea that I went to school with the famous Reichi Yurino was his name. Now I remember after reading it again. No, it's my pleasure. I make you feel good, boys. Sorry. Oh, Oni-chan, big pro, what are you doing here? Okay, an overview of linear algebra. How about right now? Well then, when would you like to start? Okay, then I don't really understand the concept of it all, and the calculations seem way over my head. Yes, that is very, very, very sad. Let's see, your brother said that you were having trouble with linear algebra. Yeah, obviously, they are at university. It is true that linear algebra is a pretty abstract subject, and there are some hard to understand concepts. Only some, like dual spaces and bivectors and the like, linear independent subspace bases. Oh no, all those things. He's just throwing them into the room right now and we don't know what they are. I am so lost at this very moment. I wouldn't say it's middle school level, but it's not too far off. Yeah. Actually, everyone can learn linear algebra. It's like, it's hard to get used to the abstract stuff at first when you start at university, but in the later semesters it's pretty damn easy. It's just the fundamentals, at least in linear algebra 1. The calculations are nearly as hard as they look. And once you understand the basics, the math behind it is actually very simple. You said it! Oh well, that's a relief! Really, where? Oh, it's going in the regular direction. Now I'm confused. But I still don't understand what is linear algebra exactly. That's a tough question to answer properly. Really? Wow. Well, it's pretty abstract stuff, but I give it my best shot. Okay, let's see. From 3 to 2 dimensions, from 2 to 3 dimensions, from 2 to the same 2 dimensions. Broadly speaking, linear algebra is about translating something residing in an Why m-dimensional space? I would always start with n-dimensional, but never mind. In an m-dimensional space into a corresponding shape in an n-dimensional space. Oh, yeah, that makes total sense. Now she understands. Whew, that was easy. We'll learn to work with matrices and vectors, with the goal of understanding the central concepts of linear transformations, eigenvalues and eigenvectors. Yes, that is good. That's a good overview of linear algebra 1. Okay, yeah, and it has certain uses in mathematics and physics, blah, blah, blah. He's getting into that. And in the next chapter, they are finally going to make out, I think. Okay, those were just the basics, and now we're going to get into the fundamentals. Okay, he's getting ripped apart once again because he sucks. Why is there even a karate club in a university? I don't understand. Okay, here's some non-canon shit. Course layout. Okay, we are starting off with the fundamentals. This is where we are at the moment. Then matrices and vectors, linear transformations, eigenvalues and eigenvectors. And now, number systems. Okay, so they are going to go over the number systems and they are going to put all of these into a nice and sorted Euler diagram. But this Euler diagram is, yeah, basically in a little rounded rectangle shape, which I really like. This makes for a very nice explanation of the whole thing, especially since they put all the most important concepts into here, where I is defined as square root of -1. I wouldn't go with this. Okay, only on the principal branch. This is a big mistake. I wouldn't do this. Definitely not. They should have said I squared is equal to -1. This makes it less ambiguous, but never mind. In normal case on complex numbers, you shouldn't use square roots. That's just bad behavior. Okay. Then positive integers, blah, 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 real numbers. Okay, I don't know for sure, but I suppose some mathematicians made it up because he wanted to solve equations like x squared plus 5 is equal to 0. Why plus 5? Why not plus 1? Never mind. But yeah, she was pretty confused about the number I suppose. Okay, next up, using the symbol, these previously unsolvable problems suddenly became approachable, right? We can put it into linear combinations. Implication and equivalence propositions. I thought we would talk about implication next, but first let's discuss propositions. A proposition is a declarative, I think it's an English sentence that is either true or false, like 1 plus 1 equals 2, quick maths, or Japan's population does not exceed 100 people. Yeah, either true or false, and then we can put all of this into truth and yeah, all of these tables and decide if an implication gives us true or false out. Then we have equivalences and all of this stuff. Basically just giving you basic logic on your way, which is good. You need this for linear algebra. This is how most courses start. And then a bit of set theory. Okay, they are probably going to say, okay, so we have a set of things like these pepper and salt, spices that we got right here, and all of these belong to the set of spices, but they are individual elements, I suppose. Yeah, it's a collection of things with things in there. That's a good explanation. And then they are going to get started with examples and exercises. This is what I really cherish about the series. They always put exercises at the very end, so you can basically solve with it things already. So they are just not going to leave it at a theory. They are also going to provide you with various problems, which I really enjoy a lot. Okay, then they go into set symbols and like subset and all of this stuff, mother set. Okay, we have two sets, and then they are going to say that some sets are included in other sets and so on. And next they are going to talk about functions. Functions being mappings, basically, which map items uniquely. Basically talking about one-to-one and onto-two. Yeah, they are going to make a mapping here where all of the people correspond to a certain type of food which they like the most. And also all of this notation here. I don't know about this notation, but this one is pretty sleek. I like it. But I rather prefer this notation. This is what I'm used to. Yeah, f is completely arbitrary. G or h would do just as well. Yeah, but we call it f for function, obviously, at first. This is what you should have said, probably. Yeah, then they are going to talk about images and pre-images. This is good. This is also some fundamental stuff. And I'm waiting for surjection and injection being introduced. The function f is a rule that says the element x of the set x goes together with the element 2x minus y in the set y. Yeah, basically. Okay, is being mapped is like the better thing you should say here. But yeah, this is like a nice little overview giving you the best of everything when you get started. Like, yeah, this is like a little calculus overview too. And then we have range and codomain, and also domain. I mean, oh yeah, they introduced the domain already, and now they are going to go into the difference of range and codomain, which is a very important difference that many students fail to understand at the start. So you really need to pay attention to what the range is and what the codomain is. Yeah, and now one-to-one and onto functions, and so surjection and bijection, and also injective functions. Very important, especially later for linear mappings, basically, in linear algebra. And then they are going to talk about composition and all the stuff. We are going to skip over all of this. Linear transformations now already. Why are they talking now already about linear transformations? I mean, yeah, this is like the most important thing you should learn in linear algebra 1. When is a linear transformation a linear transformation? If it's additive and also homogeneous. And then you can basically do a lot of funky stuff with this, especially when it comes to matrix diagonalization and all of this stuff. And in operator theory, it's a huge topic. which is really, really important. So linear transformations also gives you very easy points on exams because it's just straight up calculations, at least in linear algebra 1. Very easy mappings, very easy linear transformations. Let's have a look at a couple of examples. Yeah, for example, regular addition of polynomials is linear transformation and so on. Later we are going to see that matrices are just linear transformations in disguise and so on. Combinations and permutations, they're going to go into this too. Yeah, and then we also got an exercise question. Already we got a bit of combinatorics going on here that they are still covering. And yeah, very good stuff. This is a huge prerequisite section. This is the greatest one we have seen up until now. Great in the sense that it has the most content, but it's also a very good overview. A lot of the stuff was actually missing from the Manga Guide to Calculus, for example, and I wish some of these would have been in there, but you can't have everything. I mean, this is probably why the Linear Algebra Guide got so many good reviews online, because it just covers so many fundamentals that you definitely need for getting through a lot of university and also high school courses. Not all rules for ordering are functions. Yeah, obviously not. And now we are at chapter 3, matrices. Now it's getting exciting. But I'm still not certain if it's a rather good decision to go into matrices before vectors. But we will see how they are going to handle this one. Yeah, once again, the karate, no one cares about that, honestly. And suddenly we are dealing with the matrices. Now we are at the matrix chapter. And yeah, this video fits right with the new Matrix film that comes out, so that is also pretty fine. What is a matrix? A matrix is a collection of numbers arranged in m rows and n columns, bounded by parentheses like this. Okay, so we got an m by n matrix. Why are you doing this? I mean, m comes before n, but still, you don't do this. We always start with n. This is mildly confusing and extremely infuriating. A matrix with m rows and n columns is called an m by n matrix. Ugh, yikes. So we got a 4 by 1 matrix, which is a vector basically. Oh yeah, this is why they start with matrices, because vectors are just special cases. But still, I wouldn't do that, to be honest. The items inside a matrix are called elements. Yeah, or entries, you could say. A matrix that has an equal number of rows and columns is called a square matrix. The created out elements in this matrix are part of what is called the main diagonal. They are great for writing linear systems more compactly. Since they make for more compact systems, they also help to make mathematical literature more compact. Yeah, and they help teachers write faster on the blackboard during class. Is this the only thing that comes to his mind when it comes to matrices? I mean, that there are so many uses for them, and the only thing he has to say is, and they help teachers write faster on the blackboard during class. Stupid. Instead of writing this linear system like this, we could write it like this using matrices. Becomes this. So this, it does look a lot cleaner, exactly. This is what he understands immediately, or what they haven't even introduced matrix multiplication yet, or vectors in the first place, and they are obviously using this vector right here, and she understands immediately, why can rewrite it like this? This is just stupid. This is what I have to say at the moment. I mean, this is just a roundabout way of introducing matrices and basically their functionality. I would have started with vectors. I don't like this total ordering in this book. I don't like this part, okay? This is like a criticism I have to basically tell you guys. Writing systems of equations as matrices, yeah. I mean, it's an easy matter, but it only becomes clear when you introduce matrix multiplications. So matrix calculations. Now let's look at some calculations. The 4 relevant operators are addition, subtraction, scalar multiplication, and matrix multiplication. Yeah, obviously, this makes up a vector space, basically. Those are the most important things. So yeah, that is blah blah. We can only add equal dimensions together, you could say. Subtraction works the same, because subtraction is only addition. There's nothing new about that. Scalar multiplication, obviously we need to have so an n by m matrix multiplied with an m by k matrix to get ourselves an n by k matrix overall. So we really need to take care of that. Oh yes, it's only scalar multiplication. I'm terribly sorry. This works without any restrictions whatsoever in a vector space, obviously. But matrix multiplication is a bit more sophisticated. So we need to take a greater look at the dimensions before we can get started multiplying. He doesn't show a nice scheme of basically getting yourself the multiplication. This is not something they have done here. So they are skipping this basic step, which is a bummer, I suppose. As you can see from the examples below, changing the order of factors usually results in a completely different product. Yeah, exactly. They are not commutative or abelian in the regular sense, not in general. An m by n matrix times an n by p. N by p? Are you fucking shitting me? Who came up with those? N by p matrix, it's an m by p matrix. That's just stupid. But they are not showing a nice scheme for multiplying. So when we first did matrix multiplication at university, I never used this scheme, but it helped a lot of students. This is what I remember. They put it in some kind of cross table where they put the first matrix here and the other matrix down here, something, and then they basically got themselves the product things up here. This is what they did at university. Helped quite a bunch of students, but they are not covering something like this here. But never mind, okay. The easiest way would be to just multiply them from left to right like this. Yeah, but this is very unintuitive how they are dealing with this topic here. Special matrices. So we got probably non-singular matrices and we got a zero matrix. Okay, yeah. Transpose matrix. They introduced this also. Symmetric matrices, upper triangular and lower triangular matrices. They are very cool. They are very cool for solving systems of equations. Okay, this is like the preferred thing you want to have. Are they also called upper echelon matrices or something of that sort? I think they have that name, but that's a very useful form. And diagonal matrices, very, very important diagonal matrices, so many nice properties. They are also showing why they are so nice, exactly, because it makes matrix multiplication way nicer overall. And the identity matrix, yeah, they should have introduced the identity matrix right at the start too. So as the most important special matrix, basically, next to the diagonal ones. But never mind. Yeah, identity, they are showing why it's called an identity, obviously. And now she's pretty damn daunting, mate. She's trying to, yeah, to really make him like her. Next up, more matrices. Gather them up and sweep. Okay, I should sweep, so taking the page here and just sweep downwards, I suppose. Let's take a look at more matrices. Now here comes the inverse matrix. Explaining them without using examples isn't all that easy, but let's start explaining them without using examples isn't all that easy, but let's start with the definition anyway. Yeah, this is how you should start. If you have a inverse, then you have a left and right inverse, and you're going to get the identity out on the other side. This is like the good definition you should definitely start with in any case. Cofactor method, Gaussian elimination, blah blah blah. The calculations involved in the cofactor method can very easily become cumbersome. So yeah, we are going to skip that for now. Yeah, I understand that. And they are using Gaussian elimination to get themselves the inverse matrix here. Okay, very, very nice. I don't like this notation right here. In a normal case, what we always did at university was put like another line through that, because here you get the impression that it's like a 3x2 matrix, which it kind of is, but it also isn't, especially if you just want to get the identity out, because here in the 3x2 you don't have a strict identity, you could say. So you should definitely try to always put a line here, or just leave that out of the way at first and then try to get yourself the inverse matrix. But I see where they are going at here, because they also want to get the solutions out on the other side already. Oh yeah, and then we have to find the inverse for yourself here, and then we have the common methods, etc., also with the solution. That is very nice that they give you the solutions too this time around. Let's make sure that the product of the original and calculated matrices really is the identity matrix. Yeah, then you always have to check. This is something that you just have to do, and it's good for you if you check, because then you know if you have done everything right. Now here's the basic formula for the inverse of a 2x2 matrix. Yeah, very nice. Next, they are going to cover the determinant. The determinant in the normal case is the last thing you are going to cover in linear algebra 1, right before diagonal matrices. So the determinant is like the grande finale of any linear algebra course at first. So they are introducing it at the very start, haven't even covered group or semi-groups yet. Determinant, given a matrix, have an inverse. Yeah, they are going to say, okay, we need the determinant to determine if something has an inverse or not. But there's also obviously some kind of geometric interpretation that I still don't know and I don't care about because I hate geometry stuff and it really doesn't matter in any kind of way to get a geometric intuition. And the volume of the parallelepiped spanned by the following 8 points also coincides with the absolute value of blah blah blah. Yeah, that's like the geometric interpretation. Okay, then they are calculating the determinant using the cofactor expansion here, basically, and yeah, just the regular stuff that you're going to go through at university too, trying to spot a pattern here. Oh, they all go from 1 to the number of dimensions. Yeah, exactly. Those are like all the permutations that you're going to get. Yeah, exactly. This is a very important thing that you're going to learn. This is why you cover permutations at first in the prerequisites. Then we get a lot of tables, which are totally overwhelming. If I were to read through that book, honestly, I wouldn't read through that because it just looks extremely cumbersome. But this is just all the permutations, basically. Just putting them nicely here. You are the best. Oh my god, he's getting stronger. He can punch his fist against a stick. Calculating inverse matrices using cofactors. Yeah, this is like an absolute fucking hassle. Solving linear systems with Kramer's rule. Okay, we are already dead. Gaussian elimination as presented on page 89 is only one of the many methods you can use to solve linear systems. Even though Gaussian elimination is one of the best ways to solve them by hand, it is always good to know about alternatives, which is why we'll cover the Kramer's rule method next. Woo! Kramer's rule. That's not something that many people like, me including, I don't like it. And next we are going to cover vectors. Ooh, so exciting. Now let me guess, for the vectors they are probably going to say it's just a special case of a matrix where we have the number of columns being equal to 1. And they are probably not going to introduce vector space. It doesn't look like they introduce many abstract topics, nearly none. All they really cover are the things that you need for calculating something, so like the application kind of things. Next, vectors. What is a vector? Please don't say that it's a fucking arrow in the plane. I'm going to kill you. Oh my fucking god. I don't like when they interpret vectors as arrows. This is just so stupid. Yeah, but they are going to say that they can give you a certain direction probably. That works out, and it's a 1 by n matrix and an n by 1 matrix. Okay, you can transpose it. Basically, there are two types of vectors, you can say. I use the 1 by 2 matrix and the 2 by 1 matrix to make things simpler. Okay, yeah, they are just going to basically get yourself a linear combination of these vectors to get yourself the direction where it's going to land at the very end. Okay, basically introducing vector addition that way, and also scalar multiplication and everything, with just being a geometric interpretation. Like addition is, you go to this one point, then to this next point. This is the same as going to this and that point directly. Same with subtraction. Scalar multiplication, obviously it's a vector space. This is like just increasing or decreasing the length of your vector, or if you have a negative sign, letting it go to the other side. Or matrix multiplication, that it has some bigger geometric interpretation, probably in more dimensions. Horizontal vectors like this one are called row vectors, and the other ones are called column vectors. This is the usual stuff that you deal with, straight line and axis, etc. A plane, yeah, vectors can span a complete plane or a hyperplane. So we got many of these. This is why you need set notation for this. And then we got a vector space. Vector space, yeah, it's a space of vectors. The three-dimensional space R3 is the natural step. It is spanned by x1, x2 and x3 like this. And then you can go upwards, obviously, into an n-dimensional vector space. Yeah, like this one right here, R to the n, and we got more than that, okay? C and the like. And that's already it for vectors. Okay, more vectors. Chapter 6. Find the constants C1 and C2 satisfying this equation. So now you have to use the regular rules and see if you can solve them like this. They also give you the solutions once again. Now they have little faces drawn onto the vectors, which is also pretty kawaii, isn't it? Fucking kawaii, mate. And now they are going to talk linear independence and linear dependence. That's also a very important thing, especially for solving differential equations later and to get yourself nice linear combinations, especially for general solutions. Here are some examples. Let's look at linear independence first. Yes, the vectors are therefore linearly independent. If all of them added together multiplied by a certain scalar is going to give you 0. And all of this only holds if C1 and C2 and C3 are all 0, then they are linearly independent. Yeah, this is like the rule for linear independence. I need to think linear independence also means that geometrically they do not lie on the same line, basically, if I'm not mistaken, but you can correct me on this one. I would need to think about the numbers. Yeah, but and now we'll look at linear dependence. Yeah, because this one basically points kind of in the same direction or is superposition of the directions that we got of these two. So it lies in the same plane, you can say. So meaning we can express this vector using a linear combination of these two by a little rotation and then scaling everything up. This is why they are linearly dependent, because they lie on the same plane. This is what it says here. Then they cover bases, okay? This is what many students have problems with. Basis, finding a basis, calculating one, it's terrible. I didn't like it either. That's a basis, also geometric interpretation. All these vector sets make up bases for their graphs. Yes, yes, geometrically speaking. Linearly independence, and now basically what a base has to do with linear dependence and independence. Giving you once again this very nice little box, telling you a little overview of everything that they have covered in the previous few pages. And dimension. It's kind of obvious that the basis is made up of 2 vectors when R2 and 3 vectors when in R3. You know, I've been thinking, oh wow, I didn't think you would notice. But why is that the basis of an m-dimensional space consists of n vectors and not m? To answer that, we have to take a look at another more precise definition of bases. There's also a more precise definition of vectors, which can be hard to understand. I'm up for it. Oh, this bitch wants to see tensors. I can see that she's up for that. Yeah, talking about subspaces. Yeah, that's a subspace. Just basically the 2 conditions that you can also pack into one condition. This is like the subspace criteria. It's not a subspace. What is linear span? Oh, I hated linear span back in the days. Those were terrible, such terrible calculations. And bases and dimensions. What are bases and dimensions exactly? Then they are going to give you a better overview. Suppose that W is a subspace of R to the M and that it is spanned by the linearly independent vectors, blah, blah, blah. This could also be written as follows. Okay, it's a linear combination of these. When this equality holds, we say that the set blah, blah, blah forms the basis to the subspace W. The dimension of the subspace W is equal to the number of vectors in any basis for W. Yeah. This example might clear things up a little. Okay, and they're going to calculate things once again. Okay, cool, so we have a projection of a house. That is nice. And now coordinates. Okay, now they are covering coordinates. This should come before vectors. Oh, he's going to blush. I told you, he's blushing once again. This fucking guy. Coordinates. And now linear transformations. we are going to get into the grande finale of the chapters here. Linear transformations. Now he's basically getting stronger. See, he already has a lot of resolution in his face. He wants to get something done. He wants this beer. I skipped the page. Linear transformation, okay. Let blah 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 be two arbitrary elements from R to the n. C an arbitrary number and f a function from R to the n. We say that f is a linear transformation from R to the n to R to the m if it satisfies the following two conditions. Yeah, obviously. This is basically just doing a linear. This is basically just what we have covered in the introduction. You could say that we have the additive property and then also the homogeneous property, but this time with a certain mapping. So using the two operations in the two spaces. And then they are going to try it out. Those are also easy points and marks in an exam. Now they are going to go through a lot of examples and geometric interpretation of all of this. I'm sorry if this seems to be rushing through, but we have more than 200 pages to cover, so yeah, I don't want to stretch this out forever. If you want to see it for yourself, then definitely make sure to buy yourself such a book to support the creator guy. We study linear transformations in an effort to better understand the concept of image, using more visual means than simple formulae. Yeah. Oh, fish. Let's take a look at linear transformation of fish. Ah, nice, very nice. They also cover the rotation matrix. Very good, very good. Very nice that they are covering this. Translation, yeah, this is just an additive linear transformation, you could say. Scaling, rotation, translation. But not all of these need to be a linear transformation, right? I mean, translation, is a translation always a linear transformation? I don't think so. I think I have proven this before, that it's not a linear transformation in a classical sense. It doesn't satisfy the conditions for linear transformation. Not the homogeneous property, I suppose. Some preliminary tips. Kernel image and the dimension theorem for linear transformations. Ugh, I hated those theorems so much. Those were terrible. Dimension of the kernel and dimension of the image. That was terrible. I always hated it. But they were so damn useful once you knew how to use them properly. Many examples once again, which is very, very important, especially for linear algebra, calculating the rank of a matrix. Here they are introducing rank. They haven't introduced it before. Very curious. And last but not least, eigenvalues and eigenvectors. Next to the linear transformations, this is the one I'm most excited about. Let's see how they are going to perform there. This is like the grande finale, and they better do well there. All right. Yeah, I think he's finally going to... yeah, I've got to show them how strong I can be. Enough! Nanhu University. Damn. Thank you very much. Oh, goodness. But she's still... Oh, you'll do better next time, I know it. Oh, psyching won't accomplish anything. I'm sorry, you're completely right. Oh, goodness. This fucking guy, breaking the heart of each and every girl he sees. Anyway, today's our last lesson, and I thought we would work on eigenvalues and eigenvectors. Okay, I'm ready for anything. Whoa, whoa, whoa. Take her up on that offer. I dare you. Studying eigenvalues and eigenvectors comes in handy when doing physics and statistics, for example. Yeah, especially there. But also has a lot of mathematical purposes, obviously, when solving difference equations and the likes. At first, we need to find the image here, okay. And then we have the certain linear transformation. Oh goodness, fish is going to be, yeah, fish is turning into flunder, I would say. Because he's so flat. Fuck me. Let's move on to another problem. Find the image of blah 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 using the linear transformation determined by... Oh, they are introducing it by... Oh, now I see. Yeah. They are using it to basically say that diagonal matrices are perfect for finding images. Yeah. And this means we also, to understand images better, we basically want to find a method to diagonalize matrices, because they also commute very nicely and the like. Yeah, perfect. So you could say that the linear transformation equal to the matrix blah blah blah, transforming every point in the space like this. Okay, let's have a look at the definition, keeping those examples in mind. Eigenvalues and eigenvectors. If the image of a vector through the linear transformation determined by the matrix blah 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 is equal to lambda times blah blah blah, lambda is said to be an eigenvalue to the matrix, and blah 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 is said to be an eigenvector corresponding to the eigenvalue lambda, the zero vector can never be an eigenvector. Nope, it can be, because we got linear dependence problems, I suppose. Trivial solution doesn't work here. Calculating eigenvalues and eigenvectors. Then they are going to go through the regular thing. So with the characteristic polynomial, then taking the determinant, finding out what lambda is, and after that what we are going to do is we are going to find the eigenvectors, forming the eigenspace in the process. And once we have this, we can basically get ourselves the diagonal matrix with the eigenvalues on the main diagonal. And other than that, we also have those two transformation matrices, and its inverse basically attached to the diagonal matrix. Try using the formula to calculate blah blah blah. It actually is. This formula is very useful for calculating any power of n by n matrices that can be written in this form. Yes, yes. This is the best property of it all. When it comes to diagonalization. This is just so fucking amazing. This is like the most formidable property I have seen in mathematics. I love it. I have used it several times. It's so cool, so damn cool that you can basically exponentiate those so nicely. Multiplicity and diagonalization. We said on page, it could be expressed in this form. That isn't totally true, as the concept of multiplicity plays a large role in whether a matrix can be diagonalized or not. For example, if all n solutions of the following equation are real and have multiplicity 1, then diagonalization is possible. Yeah, but multiplicity really plays a big role, and not all matrices are diagonalizable. So correct me if I'm wrong here. For example, if an eigenvalue has multiplicity of 2, but this only forms an eigenspace with a dimension of 1, then the matrix is not diagonalizable, because the multiplicity of the eigenspace is not equal to the multiplicity of the eigenvalue. This is like algebraic multiplicity and something else. I can't find the other word right now, I'm terribly sorry. But yeah, this is something that you have to keep in mind, and you always need to check before starting the main diagonalization process. Always take a look at the multiplicity kits, stay safe. And then once again, a lot of exercises, which I really like a lot. Looks like I got here a bit early. Hey there, been waiting long. Reggie, yeah! That voice. Stop it, let me go. Ah, don't be like that. Oh my goodness, now he can use his karate style to kick those arses. Look at that. Black pages. Now it's going to get very, very handsome. This fucking guy. This fucking guy is going to kill them. No, he didn't. He just ran away because the big fat guy came and basically bashed their heads. Or he's going to show them. He's going to show them. Oh my goodness, he's doing it. Oh no, that is such a grande finale. Oh good, look at that. They're screaming for their mommy because the big fat guy came anyways, going into Super Saiyan mode. You're okay, blah blah blah. Yeah, and this ends the linear algebra guide, the manga guide to linear algebra. Nothing else that we come is except for this last page. I still don't get it. No need to get violent. You can do it, bro. I don't care. And I thank you guys for watching, and if you did enjoy what you have seen today, then why not make sure to participate in the giveaway. As mentioned before, the last letter should appear now, and this is the one that's going to come at the end of the word. Send the solution phrase over to pie3@papaflammable.engineer, and on the 1st of January I'm going to announce the winner of the giveaway. But other than that, if you enjoyed today's video, then definitely make sure to subscribe to the channel and also to subscribe to Flammable's Wood, my woodworking channel, where you can also find me basically building stuff like this in real life, which is pretty damn cool, and also support channel on stemage.eu. And until the next video, I wish you guys a flammable day. Please stay safe. Ciao. Damn boy, my camera is so wiggly today with this little attachment. Woo! It's like jelly. Ooh, can you see this? Oh boy, that's so funky. Let's rotate it. Ooh, ciao.